Imagine that we are testing a new site. We fire at the bullseye many times, not merely to count hits, but to diagnose the pattern of the misses. Start with one shot. It lands 12 centimeters left and 3 centimeters above the bull's. The log keeps those two measurements in one row. A second shot lands 5 centimeters left and 16 centimeters above. A third lands 8 centimeters right and 5 centimeters below. Every shot contributes one left-right measurement and one up-down measurement. The row preserves which two happen together. After 48 shots, the left-right errors form one bell-shaped summary, and the up-down errors form another. Imagine that the row labels are lost, but every number survives. Now reconnect the same numbers into different shot pairs. Must the target pattern stay fixed? Choose whether the two summaries fix the pattern or the pairing can change it.
I choose that the pairing can change the pattern. The two columns keep every measurement, but they no longer say which horizontal and vertical misses happen together.
Here is the result. The first pairing produces a roughly round scatter on the target. Reconnect the same recorded numbers, and the second pairing produces a cross. The left-right histogram did not change. The up-down histogram did not change. Only the partners changed. If we were diagnosing the site, those two target patterns would suggest very different failures, even though their two separate bell-shaped summaries are identical.
So each bell curve describes one direction at a time. The target also depends on which two directional misses came from the same shot.
Before we name any distribution, separate the observations from the model. A histogram counts how many observed shots fall in each range. The bars come from this finite collection of shots. A smooth density curve is different. Its height tells us how much probability is packed near one location, and its area across a range gives the probability of that range. The bars wiggle because we have a finite sample. The smooth curve is a proposed rule for the larger process that could generate future shots. For one horizontal miss at a time, the normal model is a specific smooth, symmetric bell. Its center is the mean, the average location of the miss. Its typical width is the standard deviation, measured in the same units as the miss. Once those two numbers are fixed, the entire bell is fixed. Values near the center are common, while values several typical widths away become increasingly rare. The name normal distribution does not belong to every pile of data that happens to look vaguely bell-shaped. Under a smooth, continuous model such as this normal curve, the probability of one exact value is 0. Instead, choose a band of possible misses. The area under the density curve across that band is the probability of landing in the band. A taller curve across the same band means more probability in that interval. To compare misses fairly, measure distance in typical widths instead of raw units. A miss 1 standard deviation from the mean has a standardized distance of 1. A miss 2 standard deviations away has a standardized distance of 2. The normal rule uses the square of this distance. Distance 1 contributes 1 to that square, while distance 2 contributes 4, so the density drops more sharply. Now bring the vertical miss back. One shot gives us one signed horizontal coordinate and one signed vertical coordinate. Put those two coordinates together as one point. The point is not two unrelated numbers. It is the record of what happened in one shot. Repeat that construction for every shot, and the points form a point cloud. Its center is the average horizontal miss together with the average vertical miss. This pair is the sample mean for the shots we saw. It estimates the typical center of the larger process, but it is not magically the exact center of every future sample. Change only the horizontal standard deviation. The cloud becomes wider from left to right. Change only the vertical standard deviation. The cloud becomes taller. We will use standard deviation for visible width throughout this episode. Now watch the paired movement. When a shot is farther right than average, it also tends to be farther up than average. When it is left, it tends to be down. Measure each miss from its center. When the two deviations have the same sign, their product is positive. If the average of those paired products is positive, the covariance is positive. The cloud tilts upward. Reverse the relationship. Rightward misses now tend to arrive with downward misses, and leftward misses tend to arrive with upward misses. The centered deviations usually have opposite signs, so their products are negative. If the average of those paired products is negative, the covariance is negative. The cloud tilts downward.
The opening clouds have the same center, the same horizontal and vertical widths, and almost no covariance. Yet one is round and one is cross-shaped. Does covariance tell us everything?
Covariance does not tell us everything. It detects straight-line co-movement. A cloud can have little or no linear tilt and still contain a strong curved or split relationship. We need a way to inspect the pair from more than one direction. Put a ruler through the center of the cloud. Take one shot and slide its point straight onto the ruler. The signed position on the ruler is called a projection, one number combining the horizontal and vertical misses along this direction. Repeat that slide for every shot, and the ruler gives us a new one-dimensional histogram. Before we make a statement about every direction, keep the sample and the model separate. This histogram contains only the shots we happen to observe. A smooth curve beside it represents the population rule that might have generated those shots. A finite sample can support or challenge a model, but its appearance alone cannot prove or disprove an exact every direction property. Now rotate the ruler through an elliptical cloud. At any ruler angle, combine the two misses into one signed ruler distance. For the underlying normal model, every such projected measurement has a normal distribution. That is the defining joint property. We call the pair jointly normal or multivariate normal when every ruler direction gives a one-dimensional normal measurement. Return to the cross-shaped pattern. Imagine a hidden mechanism that chooses one of two diagonal rails, then chooses a bell-shaped sign distance along that rail. Looking only horizontally gives a bell-shaped list. Looking only vertically gives another bell-shaped list. But turn the ruler to 45 degrees along one rail. The other rail projects many shots onto the center, while the first spreads them along the ruler. The hidden mechanism itself creates that sharp center pileup, so it is not sampling noise. This projected population is not normal, and one genuinely non-normal direction rules the multivariate normal model out.
So normal horizontal and vertical measurements do not automatically make the pair jointly normal. The missing condition is the behavior of every other direction. For a pair that is jointly normal, what replaces one or two standard deviations from the mean when the cloud is stretched and tilted?
The oval contours in a normal cloud are not walls that no point can cross. Each contour joins points with the same density. Moving to a larger contour means moving to a region where the model assigns lower density. The contours summarize equal density levels of the full joint distribution. First, remove the mean. Translate the cloud until its mean sits at the origin. This does not change the shape of the cloud. It changes the reference point from the page's origin to the distribution center. Now correct the shape. First, remove the slant, then rescale the unequal widths. Hold each operation long enough to compare the before and after pictures. The two standard deviations and their covariance tell us how much correction to apply. What began as an ellipse becomes a circle. Call ordinary distance in this repaired picture the corrected distance, the multi-dimensional version of standardized distance. Compare corrected distance 1 with corrected distance 2. The density falls faster at distance 2 because the rule uses the square of the corrected distance. The exact equation is shown on screen as optional notation. The spoken idea is simple. Farther corrected distance means lower density, with squared distance controlling how quickly it falls. The equation compresses the geometry we have already built. It is not a new mechanism. Here is a fresh cloud. Its horizontal and vertical histograms each look like one broad hump, but the cloud may contain structure that those two views hide. 3 candidate rulers are marked. Which ruler direction is most likely to reveal more than one hump? Choose your direction now.
I choose the ruler that points from one cluster toward the other. Along that direction, the two groups should separate and make more than one hump in the projected histogram.
That is the most revealing direction. The split projection is evidence against a single multivariate normal explanation. At the population level, a genuinely non-normal projection would rule that model out. In finite data, both smooth and lumpy histograms remain evidence, not proof by themselves. The normal model has a useful boundary. A hard edge, two separated clusters, or a strong asymmetric tail may require a different probability model. A genuinely non-normal population projection makes the joint normal model fail. With finite data, we instead ask how strongly the observations support or challenge the model's assumptions. Now return to the opening. The two separate bell-shaped histograms did not tell us which values happened together. That pairing was the hidden geometry. In one dimension, a normal distribution is a bell-shaped rule for distance. In many dimensions, a multivariate normal is the same idea after we account for the center, the separate widths, and the way the coordinates move together.